Testing, testing. 1, 2, 1, 2. Okay, cool. All right, gentlemen. So we still have a couple of minutes. I am using my microphone today, so that means I won't be able to hear your audio until the end of class. If you have questions, feel free to either type it in the chat or put it in the Q&A, and I will make sure to get it addressed. Make sure this is charged. It is not charged. T minus 60 seconds and counting. All right. All right, gentlemen. So let's see. Welcome. Hopefully everyone had a good weekend. You were able to do what you needed to do. Let me see. So I wanted to say our exam one was due less than a minute ago, right? That's the impression. That's my understanding or whatever. So with that, I plan to update grades within the week. So within 7 days from now, I plan to have the grades updated. Again, if you're just joining us, I am using my microphone today, which means that I can't hear your audio. So if you have questions, feel free to either type your questions in the chat or the Q&A. I am monitoring those sections or whatever, those areas. So with that, we're just going to go ahead and move into the next set of information. So again, pretty much our structure from here until the end is, we'll do 3 sections and then a week of testing, 3 sections and then a week of testing. And we basically do 1 section a week, right? So 3 weeks of lecture, 1 week of exams, 3 weeks of lecture, and it pretty much has that rhythm until the end. Okay, so here we're continuing chapter 1 on graphs and functions. And I think it's not displaying properly. Okay, let's back up. Matter of fact, do I need to do that? I do kind of need to do it. Let me just duplicate this real quick.
So,
and I'll fix that later. Gates.
Online math.
All right. And so we're going to be working on section 1.4, a library of functions. A few objectives here. 1, define linear functions. 2, discuss important properties of functions. 3, graph square root and cube root functions. 4, evaluate and graph piecewise functions. 5, graph basic functions. And 6, find the average rate of change of a function. All right, so basically what we're going to be doing in this section is essentially laying a foundation for graphing. Like, we've kind of explored graphing a little bit. I think that in the past, we've used like creating a table by plotting points or creating a graph by plotting points. So you create a table, choose several values of x, find the corresponding y. If it's a straight line, you will use a straight edge, and draw the line across the entire graph. If it's a curve, connect the dots with a smooth curve, things of that nature. So here we're going to have like several base functions, right? And a lot of them you already know, right? Like if I were to say, a quadratic function, you know what that looks like. A linear function, you know what that looks like. Absolute value, I'm pretty sure most of you know what that looks like, if not all. You know, you should know what square root function, right? So these are the things that we're going to be exploring. And so again, the idea here is that we're going to be laying a foundation for graphing, right? So we're starting with these collection of base functions, right? Okay. So we're going to start off with this collection of base functions with the linear function, right? So start with familiar territory. So let m and b be real numbers, then the function f of x equals mx plus b, similar to the y equals mx plus b. It's called a linear function. If your slope is 0, then the function becomes f of x equals b. It's called a constant function. So that's like y equals a number that's going to be a horizontal line through whatever b is, right? If the slope is 0, then the function f of x equals b is called a constant function. We just said that. If the slope is 1 and b is 0, the resulting function is called the identity function. So within the category of linear functions, we have two main base functions. The very first one is really the constant function. Again, that's just going to be a flat horizontal line through y equals whatever that number is, right? So the first linear function is the constant function, or it's a flat horizontal line. And then if we let the slope be 1 and our y-intercept is 0, so then our next base function is the identity function. That's like y equals x. So that's just like a diagonal line, right? So first we have a flat horizontal line, it might show up different levels or whatever. And then the second base function is a diagonal line, all right, with a positive slope. Okay. So these are the graphs of linear functions. The graph of a linear function is a non-vertical line with a slope m and a y-intercept of b. On the left-hand side, if our slope is positive, if m is larger than 0, we get a positive line, right? So notice with the image on the left, as we trace it left to right, it goes up. So that means it has a positive slope. With the image on the right, our slope is less than 0, so we have a negative slope. As we trace it left to right, the image falls, or the graph falls, it goes down, okay? So then the image on the left is our constant function. That's when our slope is 0 and y equals some number, right? So y is going to go through, it's going to be a flat horizontal line through whatever that y value is, okay? Sorry. So again, the image on the left is called our constant function. The image on the right is called our identity function. And that's essentially y equals x. It has a positive slope. It's a diagonal line. Well, it doesn't necessarily always have a positive slope, but without manipulation, it has a positive slope. Okay. Let me check the chat. I think you guys are okay. This isn't too terribly bad. I think I would like to retire this thing. I need to charge one of them. Ooh. I don't even really use that like that. Right. So here we're asked to write a linear function g where g of 1 is 4 and g of negative 3 is negative 2. Okay. So I am going to need, come on, this guy. All right. So a linear function, right? So then I don't know the time. Yeah, hopefully he'll get in. Okay. So first, right, we're given these two pieces of data, right? So the first piece of information is saying that when x is 1, the corresponding y is 4. So let's just write out that order pair. The second piece of information is saying when x is negative 3, the corresponding y is negative 2. Okay. So I'm a fan of whenever I get ordered pairs like this, I like to just label them. So I like to go x1, y1, x2, y2. Okay. So then we're asked to find a linear function. So just as a quick recap, whenever I'm working with lines, I like to have the following equations ready to go. First is our slope formula. All right.
Where did RJ go?
Let's see. So that's y2 minus y1 over x2 minus x1. Okay, there's a slope formula. I wonder if I can put it there.
Did he come in here with you? No.
Let me see. Okay. So then we have our point slope formula. We typically use that whenever we're given a point and a slope. It's going to be our y minus y1 equals m times x minus x1. And then lastly is our slope intercept. Slope intercept formula. Okay. And that's the classic y equals mx plus b. Okay. I want to shrink this down some. I think I'm going to move it though. Hopefully, I mean, it's really more so for a reference. So I'm going to do something like, see if I can get this to work. Okay, I'll put it about here. And then we got our slope formula. Okay, point slope. I know it's a little bit small, but like I said, I'm just trying to use it as a reference. So you should know this already. And I can expand it a little bit. So let me see if I go like there, like there, and I'm going to reposition this back to where it was. We'll put it there, something like that. And then, I know it's a little bit crooked, but that's okay. Now we can expand it. That's a little bit better. Okay. All right. All right. So we'll use it as a reference at the top. So if we want the equation of the line, we have 2 points. So I think a great place to start is our slope formula. Anybody already found a slope? Anybody already got it? Feel free to put it in the chat or the Q&A. All right, let's see. Let's see what the slope is, right? So again, one of my mentors would suggest I see 3/2. Okay, let's see. Let's see. One of my mentors would suggest every time we use a formula, write it down. Let me clear that out because I know that's going to distract me. I think it's pretty unanimous. I got a second, 3/2. Okay. Every time we use a formula, write it down. Let me see. y2 minus y1 over x2 minus x1. That's our slope. Okay. So our y2 is -2. Notice the use of parentheses. Our y1 is 4. x2 is -3. Okay. And x1 is 1. So it looks like we're going to get -6 over -4. Double negative becomes positive. We can factor out a 2 from everything. That'll leave us with a 3/2. Okay, so I confirm I got the same result for our slope. Now we could use point slope, but I think I'm more of a fan of using my slope intercept, y equals mx plus b. Let me rearrange this to free up some space. Just go like this. Let's go with this. Okay, come on. That's good, about like that. Okay, good. Now we got some space. Okay, I'll keep working over here. Okay. All right. So again, I'm a fan of my slope intercept y equals mx plus b. Okay. Let's see. For my ordered pairs, I feel like that first ordered pair might be a little bit easier to work with because we don't have all those negatives, right? So if we're using that, then let me see. Our slope is 3 over 2. Our x is 1. We don't know what b is. And our y is 4. Okay. So then b is going to equal 4 minus 3 halves. All right. So that's going to be the same as what? 8 over 2 minus 3 over 2 gives us 5 over 2. Okay. So we got our y-intercept and we got our slope. So then if we put those pieces of information together, our y equals, or I guess if we want g, we're going to say g of x equals our slope, which is 3 over 2, x plus 5 over 2. Okay. So this was the final result that we got. Okay. And it is a good idea to check, for instance, if we let x be 1, right? 3 over 2 plus 5 over 2 is 8 over 2, which is 4. That checks out. If we let x be a negative 3, that's going to give us negative 9 over 2 plus 5 over 2 is negative 4 over 2, which is negative 2, right? So we confirm that both original order pairs work in this linear function. So that's about the best we can do, right? Okay, let me check on you guys. I think you're okay. Okay, you guys are good. All right, let's keep moving. And here we have a type version of what we just experienced. So they found a slope like we did. They got the same result, and they used the point slope form. So if you need to see that worked out in point slope, again, you can use that whenever we have a point and a slope, and notice we still get the same result. Two different ways to get to the same conclusion, all right? Okay. So that's how a lot of it is. A lot of it, there's more than one correct way to go about it. Sometimes there are multiple correct answers as well. That happens periodically. Okay, that's fine. So increasing, decreasing, and constant functions. Let f be a function and let x1 and x2 be any two numbers in an open interval AB contained in the domain of f. The symbols a and b may represent real numbers, negative infinity or positive infinity. Then we have the following. We say that f is an increasing function on this open interval AB if whenever x1 is less than x2, this implies that f of x1 is less than f of x2, right? So we have this open interval AB. Whenever we have x1 is less than x2, then the corresponding f1 is less than f of x2, right? So graphically speaking, as we trace the image from the left to the right, the graph is going to go up, right? That's what we mean by increasing. It's similar to like how we talked about with lines having a positive slope. It's a similar notion here. This just kind of, it's because we're not working with a line, so we're working with a curve. So this is how we're going to describe. It's similar to like how we talked about positive slope. We just have, we call this an increasing function, right? So again, graphically speaking, as we trace the image from the left to the right, it increases. So if we could talk about increasing, then we can talk about decreasing, all right? A decreasing function on an open interval AB, whenever x1 is less than x2, this implies that f of x1 is greater than f of x2, right? So in other words, as we trace it left to right, the image goes down. As we trace it left to right, the image goes down. We call this a decreasing function. Okay, and then a constant function. So we say that f is constant on an open interval AB. If whenever x1 is less than x2, this implies that f of x1 is equal to f of x2. Right? So as we trace it left to right, it stays flat. It neither goes up nor does it go down. Okay. So from the graph of G, find the intervals over which G is increasing, decreasing, or constant, right? So as we move from the left to the right, initially,
after we come back, but I'm not
the graph is increasing.
Why do I have practice
today
after we get
whenever
back?
we talk about increasing, decreasing, or
I got back
constant,
from Chicago yesterday.
we're going to say, like, for instance, here we're going to say the graph is increasing over what portion of the domain. So as x moves from the far left, right?
It was all right, but I might want to.
So we're saying that this function is increasing. The far left will be negative infinity up to when x is what? Negative 2. whenever we're doing increasing, decreasing, or constant, I'm pretty sure we always use parentheses. So we always use parentheses. And so what that does, that always guarantees us at least 2 points to compare, right? If we had a square bracket, we tried to use an endpoint. If, like, for instance, if we had a square bracket on that -2, we wouldn't have a point to the right to compare to. But when we're using parentheses, we can get infinitesimally close to -2. So, we'll always have at least 2 points so we can show that the graph is always increasing in this instance. Okay. Long story short, whenever we're doing increasing, decreasing, or constant, we should use parentheses across the board. Okay. So we're saying that this graph is increasing as x goes from -infinity up to -2. Then it's what? Constant. So I'm just going to capture that like this. I'm going to say constant as x goes from where? -2 to 3. Again, parentheses across the board. And then the function is decreasing as x moves from 3 to positive infinity. Infinity always gets a parentheses because we're doing increasing, decreasing, or constant, always gets a parentheses as well. Okay. Okay. All right. Okay. So they got the same thing. So then what do we mean by a relative max and relative min? Okay. So in the previous portion, we were describing what do we mean by a function when the function is increasing, decreasing, or constant. So then I'll just go ahead and sum this up. Relative max or min is where we have our turning points, right? So that's where our function goes from either increasing to decreasing, or where a function goes from decreasing to increasing. Relative max occurs where a function goes from increasing to decreasing. It's like the peak of a mountain, the top of a mountain, right? So where a function goes from increasing to decreasing, that turning point will be our relative max. Relative min is going to occur where a function goes from decreasing to increasing. So that's going to be like the bottom of a valley. All right. So you have mountain range, peaks and valleys. The peaks would be our relative max. The valleys would be our relative min, so on and so on and so on. So if a is in the domain of a function f, we say that the value f of a is a relative min of f if there's an interval x1 to x2 containing a such that f of a is less than or equal to all f of x for every x in this open interval x1 to x2. We say that the value f of a is a relative max. Something don't look right there. Oh, okay, yeah, we're good. Yeah. So again, we're saying that it's a relative min if it's less than all nearby y values. We say that f of a is a relative max of f if there is an interval on an open interval from x1 to x2 containing a such that f of a is larger than all nearby y values for every x in the interval from x1 to x2, right? So relative min, that y value, that f of a is less than all nearby y values. Relative max, that f of a is larger than all nearby y values, okay? All right. And so, if we were looking at a graph, here we have two examples of relative max and two examples of relative minimum values. Okay. I feel like that's not too terribly bad. So we say that a function f is called an even function if, okay. So we have some more terms, right? Even function. I'd rather just describe this first before we kind of look at the formal definitions. So an even function, the simplest way to kind of identify it, that's whenever we have like y-axis symmetry, right? With even functions, whenever we have a point x comma y on a graph, if we're going to have y-axis symmetry, our y values are going to stay the same, but the x values are going to change. So whenever we have x comma y, we also have negative x comma y, right? So whenever we get a point on the right, we also get a point on the left. And so the whole image is going to be symmetric about the y-axis, right? So the y-axis is going to serve as like an axis of symmetry for our image, right? So we say a function f is called an even function if for every x in the domain of f, negative x is also in the domain of f, right? So whenever we consider f of negative x, we also have f of x, right? The graph of an even function is symmetrical with respect to the y-axis, right? So again, with even functions, that means we have y-axis symmetry. Whenever we have a point on the right, we also have a point on the left. In other words, whenever we have x comma y, we also have negative x comma y, okay? Keep in mind that with the even function, the y values stay the same, the x values change, right? Okay. So then if we could talk about even functions, then we can also talk about odd
Odd
functions, right? Let me
functions.
just do my own synopsis first. So with odd functions, so with even functions, we had what? Y-axis symmetry. With odd functions, we have, you might be tempted to say x-axis symmetry, but it's actually origin symmetry, right? So with odd functions, we have origin symmetry. What do we mean by origin symmetry? Origin symmetry is where whenever we have x comma y, we also have negative x comma negative y, right? In the previous one, only the x's change. With origin symmetry, both x and y change, right? So all points are going to be equidistant and symmetric about the origin. And the shapes usually take on like kind of like an S shape almost. But again, whenever we have x comma y, we also have negative x comma negative y, right? So all points are the same distance and symmetric. In other words, mirror images about the origin. So function f is an odd function if for each x in the domain of f, negative x is also in the domain of f, and f of negative x equals a negative times f of x, okay? The graph of an odd function is symmetric with respect to the origin, right? So we'll see these like in action momentarily, right? Okay. We don't have a function for x-axis symmetry, right? If it's symmetric about the x-axis, that means it's going to fail the vertical line test and it's not going to be a function, right? So we don't really have anything for x-axis symmetry. But y-axis symmetry, we call that even. Origin symmetry, we call that an odd function. Okay. So here we're asked to determine whether each function is even, odd, or neither. Okay. So then we're basically doing a test for symmetry. All right. We want to do a test. So the way we do a test for even, odd, or neither, what we want to do is we want to replace each x with negative x, simplify, and then analyze the result. All right. So let's see it in action. Okay. So with A, first we want to replace each x with negative x. All right. So we have our g of x equals x cubed minus 4x. All right. So I started by replacing each x with a blank parentheses. Again, what goes into the blank parentheses? We're replacing each x with negative x. So we're going to go like this, and like this. So now we use algebra, we simplify it. And we want to see if we can get it back either to the original or if we can get it to negative times the original, then we can interpret what that means. All right. So if we have a negative number raised to an odd power, take a moment. Should the final result be negative or should the final result be positive? All right. If we have a negative number raised to an odd power, should that result be negative or should it be positive? Right. It should indeed be negative, right? Okay. So we're going to just leave it as negative x cubed. Now, with that second term, we have a negative 4 times a negative x. Double negative is positive, right? So that's an example of an even number of negatives. So that's going to be a plus 4x. Is this the original? This is not the original, right? Can we get to some manipulation on the original? What happens if we factor out a negative? Let's factor out a negative. So if we factor out a negative, we're going to have x cubed minus 4x. Is this a negative times the original? Yes, right? This is a negative times the original, right? Not f, but g, right? So this is indeed a negative times the original. So we have g of negative x equals a negative times g of x. So that's the definition of what? I think that was the second one, right? That's the definition of an odd function. So g is odd. This is an odd function. That means it's going to be symmetric about the origin. So this is how we do a test algebraically to determine whether a function is even, odd, or neither. Again, a quick recap: we replace x with negative x, we simplify, and then we interpret the results. If we get back to the original, then that means that it's even. If we get a negative times the original, like we did in this example, that means the function is odd. If neither of those cases happen, then we say that it's neither. Um, Let me see. I'm going to like like this, and then I just like to resize it. Come on, thank you. Oh, come on. There we go. Can we get more here? Do we want to? What do we want to do? Let's just do another. Let's just duplicate this. Come on. What's the time? We'll let it be. Let's duplicate and clear. That's good. Okay, let's go ahead and do the next one. Okay. So then if we're working on B, let's do the same procedure, right? We want to do a test whether this function is even, odd, or neither. Right? So first thing we're going to do is replace each x with negative x. Okay. So we got our f of x, and really the first thing we're doing is replacing each x with a blank set of parentheses. So we got x squared plus 5. And again, what are we doing? We're replacing each x with negative x, negative x. Okay. I don't know. This is a tangent. I'm just talking, just something random popped in my head. I just saying it just for the sake of saying it. So, I'm always on adventures on the weekend. So this weekend I ended up doing like some DoorDash, just some drive and just pocket change or whatever, right? So, but I like to do it because I discover like so many like restaurants around the city, and it just gives me, just play money, just money to just do random things with that I want to do, right? Instead of coming out of my main budget. So, basically this weekend I discovered two like restaurants that were like interesting that I enjoyed, right? Real simple. Because like at first I had this craving, I was like, man, I want like some shrimp tacos. I was like, and I didn't even research it. Well, I actually did. I was like, oh, there's a spot. So I went to this place called Talking Tacos. But I was on my way there naturally, like without even, anything. And then on my way there, I got a ping to pick up food. I was like, oh, that's a good omen. That's a good sign. So sure enough, it was a double pickup. So I went on to order my food. I was like, how long is it going to take? They were like, oh yeah, you just order on the kiosk. It takes like 5 minutes. I was like, bet. So I ended up ordering a shrimp burrito. Oh my Lanta. That shit, that shit was so good. I was like, ah. And it took like 5 minutes. I was like, man, this is delicious. And they had like so many options. This was on Sydney Marcus, like in that area, up in that area, right? So there's a quick trip down the street and everything. But yeah, it's a place called Talking Tacos. So that was really good. Like I said, I got a shrimp burrito, and it hit the spot, man. It was good. And I usually don't do dairy, but I just let them make it the way it was, and it didn't upset my stomach. I was like, I usually avoid like cheese and dairy like at all costs. I mean, that was once upon a time. A lot of times at this stage in my life, I live vicariously through others when I see them eating like cheese pizza and all the other stuff. The smell is enough for me, but I really can't do cheese anymore. But that whatever they did, it was good, and it took like a few minutes. So I was like, I was good, and they had a whole bunch of options, carne asada, all these other different options. So I'll probably be back to try some of the other stuff. So shameless marketing, for them, they get money, but it was good. I just wanted to share it. And then the other place that I discovered, oh, what was that place called? I think it might be called Shane's Bakery. This was like near Georgia Tech. But like, so what he was, man, it was okay. First, it was overpriced, right? It was overpriced, like because I don't see myself really going back. But I was glad that I had the experience, and it seemed like it was black owned. The clerk, the guy there that was serving it, was black. So I'm not sure if it was a black owned business or not. But it's definitely an experience. And like the group that was there before me, it was like 4 people, and they were ordering 2 cookies each. So the price of each cookie was like almost $8. I was like, son of a bitch. I was like, but what it was basically a cookie ball. Like it was like almost a baseball size of cookie. And he'll like heat it up in like a little toaster oven. I mean, it was a unique experience. It was actually really good. I don't know if it was worth $8, but the people in front of me, they ordered like 8 of them. So 8 times 8, like $60 in cookies. Come on. All right. So, but it was good. I feel like if you've never experienced it, I would encourage you to experience. I think it's called Shane's Bakery or Shane something. It's like a purple pink kind of thing going. But it was an experience, right? So those are my little two discoveries that I don't mind passing on. Do your just be prepared for Shane's. The other place was reasonably priced, maybe like $15. But it was good. It was good. Like it hit the spot for a shrimp because I originally was gonna do like a shrimp taco, but when I saw they had shrimp burrito, I was like, oh, it's on like popcorn, right? So, like I said, just a random tangent, just a little bit of adventure stuff. So we're gonna bring it on back, right? Now they're not consciously using, they're not sitting down and breaking out calculations, but somebody has to like take measurements, write up recipes, baking conditions, timing, customer service, right? So communication, this is all mathematics. Money exchange, finances, you need like a treasurer or whatever, a person, an accountant, somebody to keep track of the finances, a clerk. Like these are all expressions of mathematics, the kind of stuff that we're talking about. Again, you might not break down and like do these kind of calculations, but what we're talking about is inherent. Like you think they can like do these like tap transactions or these like digital transactions without this stuff at play. This stuff is like the underlying code or the underlying conversation in the codes that we're using for like our cell phones, for these financial transactions, for this equipment, for the construction of it. So, that's why math is so interesting to me because it's like it's unassuming. We don't realize the extent of how it's being used, but it is being used, and we use it. This is actually second nature for us. We're not even aware of it, right? So, anywho, fun little adventure around the city of Atlanta. Okay, so with this one, right, we have an even number squared, right? Even number of negatives. Sorry, a negative number to an even power. So that means that final result is going to be positive. Is this the original or is this the negative times the original? This is the original. Okay, so we have f of negative x equals f of x. So that's the definition of a function being even. Okay, that's the definition of a function being even. Okay, I think I can fit C on the right-hand side here. So what I'm going to do, just kind of shrink this down just a little bit. Create some space. Okay, and let's go ahead and test C. So first we're going to replace each x with a blank set of parentheses. We're going to replace each x with negative x. Okay, and then we're going to simplify. So the first term, we have an odd number of negatives. We get this guy. Second term, even number of negatives. We get this guy. Is this the original? No. If we factor out a negative, can we get a negative times the original? No. So this is an example of something that is neither even nor odd. And it's an example of something that's neither. Okay. Another delivery I did, I like, so I like to kind of do these in like the Brookhaven. That's like around Lenox Mall area. I did a pickup from Lenox Mall. It was like the third floor up there by Legoland. And I was like, the drop off was literally across the street. I was like, and it was like $10. I was like, bet. So I was like, instead of walking back to my car and trying to drive around, I just hooked it on foot. But it got to a point where I was outside the building, but they wanted me to walk like a block around to get to the entrance. So I just like American Ninja styled it and just like hopped over the fence, I had to go a little bit ninja on them. But yeah, I got there and it was just I got the reason why they had it laid out like that because they don't want like they're trying to minimize people walking by to just get into the building. But where there's a will, there's a way, right? I was like, I'm not about to walk around this thing. Like it was going to be a long walk to get to the entrance. I was like, nope, I'm not about to do that. So, and because the door, I was literally looking right at the door, but they were trying to direct traffic way around. I was like, no, I'm not about to do that. So, like I said, I just went in ninja mode and dropped it off. And it's like, because usually what I'll do is I'll be on foot. Like I like to go running and stuff. And so sometimes depending on how close the drop off is, I'll just hoof it and just make that part of my little exercise or whatever. Okay. I'm going to keep going. So obviously, we're not going to have time to get through everything, but again, that's where my recordings come into play. Um, it's the same information, that narrative, right? So we're going to hang out for about a little over 5 more minutes, and then we'll call it a day. So here we have evaluating a piecewise function. Let me see. I'm going to do a scan actually. Actually, I'll say this part on my own. So a piecewise function here. Determine which line of the function applies to number A, and then evaluate f of A using the line chosen in step one. So for instance, in this example, we're asked to find f of 0 and f of 2. A piecewise function, what it is, it's just multiple graphs or multiple functions on one graph, right? So for instance, the first graph we have is x squared, and the second one is the linear function 2x plus 1. But x squared only applies when x is strictly less than 1. So basically when x is to the left of 1. And 2x plus 1, that linear function only applies when x is greater than or equal to 1. So if we're going to evaluate this, for instance, when we're asked to find f of 0, so then if x is 0, we ask ourselves, are we using line 1 or are we using line 2? Well, 0 is less than 1, so we would use line 1, right? So then we plug in 0 into line 1, the output is going to be 0. When we're asked to find f of 2, we ask ourselves, do we use line 1 or do we use line 2? Well, 2 is larger than 1, so that means we're going to use line 2. So then we plug it in, it looks like we get a result of 5, okay? So that's essentially that part. So then here in sketching a graph of a linear function, again, these are just multiple functions on one graph. So in this example, we have two linear functions, y equals negative 2x plus 1 and y equals 3x plus 1. So if we were going to graph this piecewise function, you can graph both of those like normal, but then you have to remove a certain portion of it, right? The first line only applies when x is strictly less than 1, so it's to the left side of 1. So any portion of that graph that's to the right of 1, you would just erase it or get rid of it. All right. The second graph, y equals 3x plus 1, only applies when x is greater than or equal to 1. So anything left of 1 for that graph, you would get rid of. Okay. If you, like, for instance, that second line has x is greater than or equal to, that's going to have a closed circle on the endpoint. The first line, because x is less than 1, that's going to have an open circle. Unless these two meet at the same point, then it's kind of continuous at that point. Right. So I just wanted to give a synopsis there. Okay, and you can see the details here or my video, right? So notice that these don't connect. You can see your open circle and your closed circle, right? This is a typo. This image is supposed to be, this is called the greatest integer function. Let's see. It basically looks like this, right? And so what this is, we want to take the value, x is going to be the value, what is it? Less than or equal to x. So it's the greatest integer less than or equal to x, right? So for instance, I just kind of want to do a few test points. Just so you can get the gist of it. So for instance, what's the greatest integer less than or equal to? Let's start with, say we had 2.99, right? So if we were to look at that number on the number line, 2.99 is between what two integers? To the left would be 2, to the right would be 3. So what's the greatest integer less than or equal to this number? What's the result here? What's the result here, right? The greatest integer less than or equal to this, the integer to the left would be 2, right? Duplicate. Okay. All right. What's the greatest integer less than or equal to 2.5. What's the integer to the left? 2. Okay. Nope, undo. All right. Undo. So what if we had like 2.00001, right? What's the integer, greatest integer less than or equal to? That would also be 2. And then whenever we have an integer, for instance, what's the greatest integer less than or equal to 2? That result will be 2, right? So if we were to plot those, all of these results would, given those different x values, the corresponding y would be 2, right? Let's do a few more. What if we had negative 3.999, right? It's just let me undo. Kind of running short on time. Okay, so there's more here. I'm going to reference my video. You definitely want to check it out. Exercise. Okay, because we're just short on time. I'm going to reference my video for this because I kind of want to scan. But you definitely want to check it out. I'm telling you now, there's a little bit of subtle things that are a little bit tricky things at play here, right? So I'm going to leave the other half as a discovery for you. We got a little over a minute. Again, you got to change all those symbols to look like that other symbol like we had a moment ago. So you just have to fix those symbols. It's just not printing. And so the whole point of the greatest integer function, we call that a step function. It's a piecewise function, but the image looks like this. It looks like the stairs on a step gate, the stairs on a staircase, right? The steps on a staircase. So we call this a step function or a piecewise function. This is called the greatest integer function. We call it a step function because the output looks like the steps on a staircase. Okay. All right, let me do a scan here. This is what I was trying to get to. So here's our collection of basic functions. We opened up with a constant function, a flat horizontal line. We have some properties there. Again, it is a good idea to watch the videos for this stuff. We have our identity function, which is y equals x. Okay, we got some properties there for you to investigate or discover. The next base function is called our squaring function, which is y equals x squared. It's a parabola. That's a classic one, right? So, what's the domain? What's the range? It wouldn't hurt to do that exercise, answer those questions. Okay. Then we have our cubing function, kind of like the S, like we talked about. Okay, it looks like this. Here's an absolute function, absolute value function. It looks like a V. Okay. And again, it's a good idea to kind of watch the videos pertaining to this. Another classic one is called the square root function. The way I remember the square root function is like the top half of a sideways parabola. Again, watch the video on that because there's some details and nuances there. Then we have the cube root function. It looks like this. The reciprocal function is another one that tends to pop up. Okay, it has a horizontal and vertical asymptote. The step function is one we did just a moment ago. And then for our purposes, whenever you see average rate of change, that's essentially finding the slope between 2 points, right? So if you ever see average rate of change, for our purposes, that's just finding the slope between 2 points. So the difference quotient is an application of an average rate of change that leads into this concept in calculus. This is a precursor for something that we talk about in calculus. You definitely want to be sure that you watch the video pertaining to this as well. Again, this is all in my pre-recorded lecture. I'm just doing a quick scan. Okay. All right. Are there any? I'm going to go ahead and remove my microphone. Are there any burning questions before we go our ways? Okay. I'll just sit here for the time being. Let me go ahead and make a copy of this available. It's right here. Fall, traditional. Let me do some closing announcements, and then we'll get out of here. Updated daily. That looks good. We're gonna load it there. Okay. So when this little pop-up window closes out, you'll be able to access a copy of anything that you saw me writing today.
I want to say this section does have a lab component, so hopefully everybody by now has connected with Dr. Lamar and followed her instructions on the lab. So again, we have it's essentially two separate classes. What we do, is in my math lab. That's where our homework, quizzes, and exams. I put all of our assignments in that one location. We just finished out exam one, so I'll update grades within about a week or so to include exam one. And then the other portion again is the lab with Dr. Lamar. Are there any burning questions before we go our separate ways? On Wednesday, we'll just go through as many corresponding homework questions for this section, and we'll proceed like that. Okay, so if there aren't any burning questions, we're going to go ahead and end the session here. And for one beautiful mind to another, enjoy the rest of your evening, and we'll be back on Wednesday, same time, same place for the next installment. Take care, gentlemen. Peace.